In this video, we'll talk about graphing complex numbers, and then we'll see what multiplication by I does to the graphs. So let me get my document camera up. Let's say we want to graph or visually represent a complex number, a plus bi. So the number line is what we're really aiming for here, but a single line isn't going to cut it. To represent this number, we have to represent this A, and we have to represent this B. Well, fortunately, we already have a way to visually represent a pair of numbers. So as opposed to the real line, we have the complex plane. And we graph points on the complex plane as the real part, comma, the imaginary part. So we have a real axis, and we have an imaginary axis. And if we have something like 3 plus 2i, we graph it as the point 3, 2. 1, 2, 3. 1, 2. Here's 3 plus 2i. I'm going to be switching back and forth between this and Desmos.com. So instead of thinking of this as the Cartesian plane, we can think of it as the complex plane. And this point, 3, 2, represents the complex number 3 plus 2i. And what I'm going to do, which might not seem very motivated when I do it, is that I'm going to multiply 3 plus 2i by the imaginary unit. The question of why I'm doing this will be answered by the end of this video. For now, just humor me. So I squared gives us -1, and this is -2 plus 3i, which we can visually represent on the complex plane by plotting the point -2, 3. And let's label it. This isn't just -2, 3. It's in fact that complex number. I'm going to repeat this process. Now I'm going to take this and multiply it by the imaginary unit I. And this just distributes multiplication over division. This I squared becomes -1. We get -3 minus 2i. And let me graph that for you. -3, -2, label it. -3 minus 2i. And we'll go back to the document camera and repeat this process one more time. We'll take the number we just found, actually 2 more times, but we'll take the number we just found, we'll multiply it by I. This multiplication distributes over this subtraction. I squared becomes -1. This negative and this negative cancel. And we get 2 minus 3i. Let's throw that up. This is plotted just as 2 negative 3, but it represents 2 minus 3i. Back to the document camera, and now this really is the last time. We'll multiply this new complex number we got by I, 2i minus 3i squared. I squared gives us -1. This negative sign and this negative sign cancel. 3 plus 2i. 3 plus 2i is what we started with. So we multiplied this by I, did it again, did it again, did it again, and wound up right back where we started. Multiplication by I just rotates by 90 degrees. Let's get that graph back up there. So we start in the first quadrant, we rotate by 90 degrees and wind up in the second quadrant, rotate and wind up in the third quadrant, rotate again, wind up in the fourth quadrant, rotate again, wind up back where you started. And this is the key to understanding why complex and imaginary numbers show up in situations you might not expect them to. Because they give you rotation. If stuff's moving around, if stuff's rotating, then complex numbers are almost certainly involved behind the scene. So if you have circular movement or sort of semi-circular movement, you really have complex and imaginary numbers lurking in the background. So for example, we're not going to get to see this in this course, but in differential equations, we look at predator-prey models. We have a predator animal population and a prey animal population, and we study how those populations change over time. And to do that, we need imaginary and complex numbers. And your first instinct might be, well, how can that be? I mean, these aren't imaginary species. They exist in the real world. And the answer to that is yeah, but it turns out that what happens if you look at the prey population and you look at the predator population and you look at how they change over time, as time passes, these populations change and we see this circular movement. For a while, there are a few predators and a medium number of prey animals. The number of prey animals and the number of predators increase together. The number of prey shrink while the number of predators increase. The number of predators and the number of prey both shrink, and then the number of prey increase while the number of predators decreases. And just because we have this circular movement, complex and imaginary numbers show up. So these aren't some kind of super obscure things that only show up in quantum physics or whatever. They show up in almost every applied branch of mathematics, just because things rotate and move in circles all the time. And if you don't retain much from this section, I'd like for you to retain that imaginary numbers, far from being some kind of weird mathematical fake thing, show up everywhere. They show up in population dynamics, they show up in transistor radio frequencies, they show up in spring movement. I mentioned that previously because springs, if you look at their height's rotating up and down and back again, and that rotation gives you complex numbers. They're just a really powerful tool that deserved better than to have the word imaginary assigned to them.